Hello. I'm early today, and so are you guys apparently. Welcome back to class, our last class of the semester. Wow. So let me know who's here. Say hi in the chat. Then we'll get started in 3 minutes or so. James says, "Here we go. Final calc class." Navik, hi. Can't believe this is it. Reagan, hi. Turner, the last sip. Yeah. Yeah. Jax is sad that it's the last class. It's been a good run. I wish we didn't have that week. I wish they didn't take that week from us back at spring break. Would have been nice to talk about the area between curves or Newton's method. Will I still be streaming something instead of calculus next week? Probably not next week, but I have some plans for after that. Haven't had anything finalized yet. But I might be back to streaming in 2 weeks. Not that I'll have anyone watching. Hello, Jared. Summer class? Well, I'm not teaching this summer, Turner, but I might just, what else am I supposed to do? You know what I'm saying? I'm stuck in a tiny apartment. Surprise stream when you hit 1,000 subs. I'm afraid that 1,000 subs isn't going to happen until the fall. Right? Who in their right mind would subscribe to a math YouTube channel in the middle of the summer? Hopefully, maybe because of the lockdown, people will subscribe, but I'm not optimistic about that. Hello, Lauren. Welcome back. Well, we're getting close to 1,000. I'm hoping to pass 800 today. All right, well, we'll start in half a minute or so. So maybe change the channel to a mustache channel. Yeah, not a bad idea. You should be able to get a lot of new subscribers now with the 2 final review videos you made. Yeah, we're going to talk about that in a second, Jax. All right, it's 10 o'clock. So if anybody wants to join in on our final simultaneous sip of the semester, now is the time to do so. Just as good as the first day. All right, let me know in the chat who joined in on the sip. All right, and then also let me know in the chat. Chat is silent. Maybe nobody did the sip. Okay, there it is. Let me know in the chat. What do we think of the video? What do we think of my final review? Was it intense or what? Let me show you this. An actual prop from the video. Pretty good, don't you think? But seriously, okay, ignoring that first scene, which was, as Jared says, intense. In that video, in the description of that video, there's an old final exam from Calc 1. So I would recommend If you have a printer, print it off. If you don't, just kind of work. The spacing is, if you have a tablet, you could write and fill it in there. It's got 18 questions. You'd have 3 hours to complete that. And so to practice that, and then you could watch the video to see how I work out the solutions. I can't believe you actually found the exam. Yeah, I had to do a lot of sneaking to get that. I have my contacts though. All right, and also, think about the channel. Make sure to share it with your friends that aren't in this class. I know you have a lot of friends that are taking other calc classes. They'll probably find it useful as well. They get to see my acting skills. Sam's a little late to the sip, but he joins in. All right, enough talking unless you guys just want to chat the whole time. What do you guys want to talk about in terms of math? What types of questions should we do? Or is there a specific question you want to cover? Let's just sip the whole Tim. Is there any specific topics? I mean, I could find a question if you just have a topic you want to cover. Okay, 48 on the Calc 1 final review packet. Jax, you're going to have to type that out. I don't have that. I don't have that anywhere other than my computer, but I don't want to break the stream. I think I'll be able to put together the dots, unless I don't want to risk it. Yeah, okay, I'll do a related rates question while you type that out, Jax. All right, so let's do related rates. All right, here's an easy one, but it's a good to get us in the right mindset. It says each side of a square. Okay, so we have a square. Each side is increasing at a rate of 6 centimeters per second. At what rate is the area increasing? When the area is 16 centimeters squared. Okay, so think about this. And while you do that, I'm going to go to my iPad and see if I could find that review sheet. I might be able to get it, Jack, so you could work on this question. Okay, so we have a square with the sides increasing. It's basically what the problem is saying. And feel free to put in the comments if you have a solution. We'll work through it in a second. I really want to find this thing, though. I just don't know where it is, though. All right, I'll have to keep looking. But so, Jax, maybe you have to type out the question. Okay, so each side is increasing at a rate of 6 centimeters. Let's call the sides x. Each side is the same. And we're given that dx dt is equal to 6. Right, and the area is x squared. So the rate at which the area is changing, that's the derivative, not 2a. The derivative of a is equal to 2x dx dt. All right, where do we go from here? Yeah, we could plug in 6 for dx dt, but that doesn't help us totally. We still need x. How do we get x? Plug in negatives. I plug in 16 for a. Plug it in here, right? To get x. And we can't. It doesn't make sense to have a negative length, so x is equal to 4. And so dA dt, so the rate at which the area is changing, is equal to 2 times 4 times 6, which is 48. All right, I'm going to risk it. Let's see, am I still live? I hope so. I'm going to try to find this review packet. Oh, Jack's typed it out. Okay, hopefully I'm still live. Find m and n such that the following function is continuous to x. Okay. Oh, sorry, you had to type this out. But this is a good question, right? It tests if we understand limits and continuity. So m for when x equals 2. Okay. Yeah, so we have this function. And it has 3 components to it, 3x minus 8. M. And x squared minus x plus n. And we want to make our function continuous. Okay? How do we do that? How do we make our function continuous? What properties need to be satisfied in order for a function to be continuous at a specific value? X equals 2 in this case, right? That's what it was telling us. So what needs to be satisfied? Right, didn't we just do a question like this yesterday? For a function to be continuous at 2, we would need the limit as x goes to 2. We need that to exist. We need, oh yeah, Jax typed it out. We need f of 2 exists. And we need the limit as x goes to 2 of f of x to equal f of 2. Right, those are the conditions that need to be satisfied. So let's just find m and n that make these satisfied. So to find the limit as x goes to 2, we'll have to take the limit from the left and the limit from the right. So the limit as x goes to 2 from the left of f of x, which one of these components, which one of the parts do we use to evaluate the limit as x goes to 2 from the left? The top one, yes, thank you. Right, because we're taking values slightly less than 2. So here. So that would be 3 times 2 minus 8, which is negative 2. Okay, and now similarly with the right, which function do we use? Which function do we use to evaluate the limit from the right? So we want to plug in values slightly larger than 2. Which one of these domains is slightly larger than 2? The bottom one, the bottom one. Good. So when we do that, we get 2 squared minus 2 plus n, which is 2 plus n. Okay, and so we want this limit to exist, right? We want the limit to exist, so the limit from the left has to equal the limit from the right. So negative 2 is equal to 2 plus n. Subtract over the 2, we get n equals negative 4. Okay? That's the first condition. And we already found n. That's great. Next, we need f of 2 to exist. So what in this case, what does f of 2 equal? Or how do we find f of 2? Yes, it's m, right? F of x is equal to m when x equals 2. So that's saying f of 2 is equal to m. Okay? So this, check this off, and then we need the limit as x goes to 2, which is negative 2, to equal f of 2, which is m. So there you have it. So n equals negative 4 and m equals negative 2. Got a smile from Jax over that one. It was a good question, right? What's nice about these last few days is in my linear class, we've been doing integrals. And today in calc, we're doing systems of linear equations. So that's cool. Crossover episode, I guess. Any other, anything else we want to go over? We did that yesterday, Max. So watch yesterday's stream to see how we do number 5 on the last exam. Should be the first question we did yesterday. Yeah, no, that's fine. I had most of your classmates have do the same thing. I would say it's not a big deal if you don't watch it daily. Can we do absolute max and min with concavity? Oh, so testing to see if you have a max or a min using concavity? Sure, we could do that. So that's the second derivative test. All right. Let's see if I could find an example here. So would you rather find absolute max and absolute min? Or would you rather test to see if a critical number is a max or a min using the second derivative test? Limit as n tends to infinity of n plus n squared plus n to the third plus n to the n over 1 to the n plus 2 to the n. You want to know if that converges or not? Second option. Okay, second derivative test. Give me a second. I gotta find a good question. Okay, I found one. We'll see how this looks. Hopefully the numbers are clean. Okay, so we have this function, 3x to the fourth minus 4x to the third minus 12x squared plus 1. We want to find the critical numbers and then state what the second derivative test tells us about the critical numbers. So does the second derivative test tell us we have a max? Does it tell us we have a min, or does it tell us that we're neither? Okay, that is the word derivative. As for your question, Namit, maybe try doing some sort of ratio test to see if that converges or not. Okay. Yeah. So the question is, how do we do this question? Does somebody want to explain how we would find the critical numbers, and then how do we use the second derivative test? Yeah, so let's find the derivative of our function, set it equal to 0, and then we'll solve. Oh, we got an x to the third here. Hopefully this can factor easily. I think it will. Set it equal to 0. So we'll factor out a 12x and then see what we're left over with. So this actually factors pretty nicely. I'm glad we got lucky like this. In general, we don't know how to factor cubics. So if you were handed a cubic and expected to factor it, chances are an x will pull out of it. So don't get stressed about factoring cubics. If you're handed one on the test, it should be pretty straightforward. I know you've probably learned a bunch of techniques of how to do that in pre-calc or algebra 2, how to find like rational roots of cubics, but don't worry about that. Okay, so we could factor this polynomial, this quadratic. And we get our critical numbers are 0, 2, and -1. Okay, so what we want to do is to use the second derivative test, we want to find the second derivative. So that's 36x squared minus 24x minus 24. And now we're just going to check, is our number positive or negative at each of these points? Okay, so f double prime of -1 is 36 plus 24 minus 24, which is 36, which is greater than 0. F double prime of 0 is 0 minus 0 minus 24, which is minus 24, which is less than 0. I'm not sure what f double prime of 2 is, but I'm fairly confident it's positive. Right, it's going to be like minus 3 times 24, and this is 4 times 36. This is a bigger number. I don't know what the number is, but again, it doesn't actually matter. We just care if it's positive or negative. Okay, so what can we conclude from the second derivative test? What's the conclusion of the second derivative test? We just found that why are we not testing the intervals? Just because, I mean, you could, Jax. But the question asks for use the second derivative test. That's a good way to check your answer. If it didn't tell us how to find if it's local max or local min, then use whatever method you'd like. But it's good to know how to use the second derivative test, so we're gonna use that. Yeah, so if I think you mean the second derivative is positive, right? That means we're concave up. Okay, our graph is going to be concave up, so the critical number will be at a bottom. I'm having a hard time with this camera. So if we're concave up, if our second derivative is positive, we're concave up, so our critical number corresponds to a local minimum. And similarly, if we're concave down, the critical number will be a maximum. Is this a little bit familiar? So this would be like this, and like this. Okay, so our local minimum is at the point -1. And then when you plug in -1, you get 3, 7, -5, -4. You get a local maximum at 0, 1, right? 0, 0, 0, 1. And then you get another local minimum at 2. Yeah. Whatever this number works out to be. When you plug in 2, and so if somebody has a calculator and wants to plug in 2, that would be great. I'll try to do it in my head, but it's going to fail. Okay, here's my guess. It's now on the permanent record of the internet. I don't know if I'm happy with it. What exactly do these numbers, 36, negative 12, etc., mean? It basically tells us how curved, how much curvature we have. Negative 31, are you kidding me? Where did I make a mistake? 48 minus 32, oh, it's 16. Okay, there's one of my mistakes. Well, we'll just say there's a lot of them. So minus 31. Yeah, so the second derivative tells us it could be a very, if it's a kind of a wide arc, then the number is going to be close to 0. If it's sharp, then it's going to be a large second derivative. So in this case, since this 36 is relatively big, well, that's not a good drawing, but it's going to be a pretty steep second derivative, or a pretty steep curve. Right? This is saying that the derivative is changing quickly. Yeah, so Jax, what you said though, why aren't we testing the intervals? That's a perfectly fine strategy for this if we weren't given this condition. Okay, so what you would do is you'd find your critical numbers, break up the number line, kind of like what we do for curve sketching, right? Break up the line and check in each segment, is the derivative positive or negative there? And then whenever it goes from positive to negative, we have a max. If it goes from negative to positive, we have a min. I mean, sometimes you're handed both the derivative and the second derivative. So it's just quicker to do the second derivative test. But if you like testing the sample points, it's perfectly fine. The test values, I guess we called them. All right, what else should we talk about? Could you do an optimization problem that relates to volume or surface area of a cylinder? Yeah. Okay, let me find one in the book. I just opened it up to the optimization section. Did we ever have any that were? Are you talking about? Would you be fine just working through that cylindrical can question we did in class, or would you like a different example? See if I could find another example. I mean, there's a few in the book, but they're way harder than anything you'll see. If you want to do a really hard question, we could do that, but or if there is something about the volume of a shape changing. All right, let's work through that one that we did in class, just as a reminder. There's not a ton of good volume questions with optimization that are like of the difficulty that we'll see for the final. Okay, so we had a cylindrical can can be made up to, it holds 1 liter of oil, which is 1,000 centimeters, cubic centimeters. Okay, and we want to find the dimensions to minimize the cost of the metal. Okay, and this is a cylinder. Okay, so what is the volume? What is the volume of a cylinder? Anybody remember this? The volume of a cylinder is pi r squared h. Okay, so it's the area of the base times the height. So you get the volume, right? Area of the base times the height. And so let's say we have a cylinder here. The surface area is equal to, well, there's a bottom and a top to the cylinder. Okay, so both of those circles have area pi r squared. So there's 2 pi r squared. And then the area of the surrounding part of the actual side of the cylinder is the circumference of the circle times the height. That will give you the entire area of the side of the cylinder. So that's plus 2 pi r h. Okay, and we want to optimize this equation, right? We want to minimize the surface area. Well, we know the volume is 1,000. What can we do? How do we go on from here? Yeah, let's solve for h and sub it into here. So h is equal to 1,000 over pi r squared. And so a is equal to 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Pi's cancel, one of the r's cancel. Right, and now we could take the derivative and set it equal to 0. Mr. Wesselcouch, are you on LinkedIn? No, I'm actually not on LinkedIn. So we take the derivative. Set it equal to 0. And the way we find when this is equal to 0, we're also going to have to find when it's undefined, just to be careful, right? Our critical numbers appear when either our derivative is 0 or undefined. So we'll take our expression here, get a common denominator to get one big fraction. And then when the derivative is 0, that means the numerator is 0. If the derivative is undefined, that means the denominator is 0. Okay, so A prime is equal to 4 pi r to the third minus 2,000 over r squared. And now we want to figure out when this is 0 or undefined. So if A prime equals 0, that means 4 pi r to the third minus 2,000 is equal to 0. Okay, and so that tells us that r to the third is equal to 500 over pi, or r equals the cubed root of 500 over pi. Which is definitely a possibility for our answer. If A prime doesn't exist, that implies that the denominator, r squared, equals 0. Which tells us that the radius equals 0. Which doesn't make any sense, right? You can't have a can with 0 radius and have it have volume. That would be out of the domain of h. So here's our answer. Radius is equal to the cubed root of 500 over pi, and h is equal to 1,000 over pi, the cubed root of 500 over pi squared. I know these are messy numbers, but you could just leave it like this. I don't want you to simplify at all. Yeah, so sorry, Jax, that we didn't get to do a new question, but I'm assuming maybe we forgot. Like a lot of you don't even remember doing this question in class anyway, so hopefully it feels new. But typically for a Calc 1 class, it's hard to come up with like volume questions that aren't like dealing with a rectangular box, right? Because typically volumes depend on 3 variables. And so you would need a lot of constraints to simplify it down to a 1 variable problem. When you take Calc 3, if Dr. Y is in the chat, I don't think she is. When you take Calc 3, you'll get to do some questions optimizing surfaces or volumes that are a little bit more complicated. All right, well, I'll stay around and answer any last minute questions. But I think that's a good place to stop. I may have had on the syllabus that we had a quiz today, but obviously we obviously don't have a quiz today. That was a mistake. So sorry if you thought there was a quiz. Make sure, as Navik says, make sure to smash the like button before you get out of here. It's good luck on the final. What else? Take a look at that video. I mean, I know I love promoting my own content all the time. But so this is it. But I'm being serious. This video I posted yesterday is probably one of your best resources you'll find on YouTube, because it's questions that it's very similar to what you'll see next week. Is there going to be another late night extra help session before the final? Jared, nothing official yet, but I'm thinking Sunday night. Okay, we're going to have ratings that compete with Sunday Night Football. That's how popular it's going to be. How much is the final worth of our grade? Check the syllabus, Jax, but I think it's 25%. And if it's better than your lowest test score, then it could be up to 35%. Any last thoughts from anybody? Your final calculus class. You did it. Some say it couldn't be done. It's been an honor. Standing ovation. Smash the like button for extra good luck. Exactly. No problem, Bella. Thanks for being a good student. Molly with the triple dab for the final class. We will miss you. Thanks for the good semester, everybody. I'm going to sign out now. Send me an email if you want to chat over office hours at all before the final. What am I going to do every morning? You know, I literally have the same issue. Hold on, I'll be back. I've been reading through this book, so hopefully maybe we could get some of these streams coming up. Analyzing baseball data with R. Could be a good stream, don't you think? All right. On that note, I'm out of here. Send me an email if you'd like to chat over Zoom. But yeah, good luck studying. Expect an email from me talking about office hours after dark. All right. Bye-bye.